Hey everyone, welcome back to the channel The Unib. Did you ever wonder how the chips inside your phones, laptops, and smart devices manage to pack billions of transistors into an area smaller than a fingernail? We often talk a lot about chip design, the architecture, the logic, and the RTL. But without actually manufacturing the hardware, none of this would ever come to life. Everything finally comes down to advanced fabrication techniques. So, today, as a part of our series exploring the world of integrated circuits, we are going to look at how a chip is fabricated from the beginning to the very end. Fab engineering is a rapidly growing field that must go hand in hand with design engineering to bring a chip to life while meeting today's aggressive market requirements of higher performance, lower power, and smaller area. One very important thing to understand about fabrication is it is not ideal. Unlike simulations, the real world is full of variations, defects, and uncertainties. Devices don't always behave exactly as expected, and the processes rarely repeat perfectly. On the top of that, fabrication is performed at a massive industry scale where yield, cost, and economic balance matter just as much as physics. In many ways, fabrication is a real war. Engineers constantly fight against defects, process variations, contamination, and yield loss. And yet, it is precisely this struggle that makes fabrication such a fascinating and critical part of VLSI. If we briefly look at the history of semiconductor fabrication, the evolution is largely driven by how manufacturing techniques adapted to enable scaling. Early integrated circuits relied on simple photolithography with feature sizes in the micrometer range. Over time, advances like projection lithography, deep ultraviolet lithography, and immersion techniques enabled scaling into the nanometer regime. As traditional methods approached their physical limits, the industry introduced increasingly complex solutions like multiple patterning and advanced process controls. More recently, extreme ultraviolet lithography, operating at a wavelength of 13.5 nanometer, entered high volume manufacturing, enabling advanced nodes such as 7 nanometer, 5 nanometer, and beyond. This progression highlights how innovation in fabrication, especially lithography, has been the key driver behind modern VLSI technology. Now let's understand how a modern chip is actually fabricated. The process begins with silicon, refined from sand into ultra-pure material and grown into single crystal ingots. These ingots are sliced into thin wafers which serve as the foundation for all subsequent steps. A thin oxide layer is grown to provide insulation and surface protection. Photolithography is then used to transfer intricate circuit patterns onto the wafer using light-sensitive photoresist and masks. Etching removes unwanted material, while doping or ion implantation introduces controlled impurities to form N-type and P-type regions. Thin films are deposited using techniques such as chemical vapor deposition, physical vapor deposition, sputtering, and evaporation. Multiple metal layers are added to form interconnections, and chemical mechanical polishing ensures a flat surface after each layer. These steps are repeated many times, gradually building up billions of transistors and interconnects on a single chip. All of this takes place inside clean rooms, which are absolutely critical to fabrication. Even a single dust particle can destroy multiple devices on a wafer. That is why fabrication is performed in highly controlled environments where air purity, temperature, and humidity are carefully regulated. Engineers wear full clean room suits, not to protect themselves but to protect the devices being fabricated. As a part of IC Design and Technology curriculum at IIT Hyderabad, I've had the opportunity to gain hands-on experience with real fabrication processes. Inside a class 1000 clean room, we explored solvent cleaning, photolithography, electron beam lithography, sputtering, chemical and physical vapor deposition, and several other core fabrication steps. This experience clearly showed me how different fabrication is from simulations and theory. This is where real world effects truly matter. Our campus also has several advanced fabrication and characterization facilities, including electron beam lithography systems, photolithography mask aligners, plasma based etching systems, deposition tools such as sputtering and evaporation systems, semiconductor device analyzers, probe stations, wafer bonding platforms, silicon etching setups, critical point drying equipment, acoustic microscopy systems, and inspection tools. In addition, programs like Spark NanoX provide students with exposure to fabrication in real world environments. One very encouraging trend is that more and more students are now gaining practical understanding of fabrication, which directly makes better engineers and more robust technology development. Looking towards the future, fabrication technology is evolving beyond traditional scaling. Emerging trends include three-dimensional integration, chiplet-based architectures, gate-all-around devices, advanced packaging, new materials beyond silicon, and continued innovation in lithography and process integration. The focus is shifting from just shrinking dimensions to optimizing power, performance, and reliability in entirely new ways. From sand to silicon, fabrication is not just a simple journey. It requires immense human effort, precise machinery, advanced engineering, deep scientific research, and enormous investment. All of this has a profound impact on the VLSI industry and on technology as a whole. VLSI remains one of the greatest achievements of modern engineering, powering everything from consumer electronics to communication systems, healthcare, and space technology. This video focused on fabrication, and in the upcoming videos we'll explore other VLSI process steps in deep. Until then, stay tuned, like, share and subscribe to The Univ.